Considering these studies together, how do lattice defects limit the overall electrochemical performance of PB-based materials? And what further experimental or theoretical investigations might be necessary to systematically address and resolve these defect-related challenges? Finally, how might future research leverage the knowledge gleaned from transition metal doping and defect mitigation to produce PBA's cathode materials that not only meet the rigorous performance demands of modern battery applications but also deliver consistent chemical composition and structural stability under demanding conditions, thereby paving the way for more effective and economically viable energy storage technologies? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How does the in-depth study of the new PBA lattice structure inspire the exploration of various structure and morphological optimization methods, and in what ways do techniques like surface modification, nanostructure design, element doping, and morphology control contribute individually and synergistically to further improve the performance of Prussian blue analogs? What underlying principles govern the optimization of these materials, and how does each method, whether it is tweaking the surface properties or fine-tuning the internal nanostructure, affect the efficiency and stability of sodium storage in the PBAs? How can changes at the atomic and molecular levels, such as those introduced by element doping, lead to enhanced electron transport and ion diffusion pathways? And what are the potential trade-offs between achieving an optimized structure and maintaining the inherent framework integrity of PBAs? In what ways does controlling the morphology of these compounds, including particle size, shape, and distribution, impact the overall electrochemical behavior and sodium storage performance of the material? How might the integration of these optimization techniques address challenges related to material defects, structural disorder, or capacity fading over repeated cycles? And what experimental evidence supports the effectiveness of each method in enhancing the electrochemical performance? What role does the open framework structure of PBAs play in facilitating rapid and reversible sodium ion insertion and extraction? And how do optimization strategies further leverage this open architecture to improve energy storage efficiency? How can the insights gained from the sodium storage performance data guide future efforts in designing PBS-based cathode materials that meet the rigorous demands of actual battery applications while keeping production costs low and scalability feasible?